Hi, and welcome to Lesson 1-7, Function Notation. So we're going to start out with some terms. We're going to look at what function notation is and the types of variables that can be represented. So function notation is another way of actually writing a function. We're used to seeing y equals 3x plus 1, but what we're going to do is replace the y with f of x, and that is function notation. So it does represent the y, the output variable, but it gives you an idea of what was input along with what it actually equals. So the input is the independent variable or the domain value that was put in, and the output is the range value or the dependent variable that is taken out. So let's see some examples where we just have to evaluate using function notation. In this example, we're given an expression for our function. So this is a function written in function notation. It just says take 7 and subtract 2 times the input. So all I have to do is put 0 in for x and evaluate. I put 1/2 in for x and evaluate, and I put -2 in for x and I evaluate. And what that does is it gets me a result of 7, 6, and 11. And these are the answers that are actually written in function notation. So f of 0 is 7, meaning the input was 0 and the output was 7. F of 1/2 is 6, and f of -2 is 11. And all I did was I did all of these calculations. I did 1/2 of 2, and then 7 minus that number is 6. Now, if you're given a graph, you can still evaluate f of 0. You would just come at the x equals 0 and go up until you hit the red line, and then that is your output. So it's 4. And for f of 1/2, you go to 1/2 on your x axis, and then you go up until you hit the red line, and that is at 3.5. So f of 1/2 is 3.5. And then f of -2, you go to -2, you go up until you hit the red line. That y value is +2. So these are the results for that. So let's take a look at another way to use function notation. And this is where we're actually going to be graphing a function. In this example, it says graph the function that represents the maximum recommended heart rate for women by age. So notice what they've done is they've given us a mapping diagram. So essentially, this is the point 0, 209, 10, 202, 20, 195, 30, 188, and 40, 181. These all represent points. This is the x value, this is the y value. So all we would need to do is set up a graph, and we would just need to count consistently. Notice what they've done is because all of these numbers are over 120, is they've squished down this y-axis, and they start counting at 120, and then they count by 20s from there. So 0, 209 would be about here. 10, 202 is about here. And they just put all of these points on there, and that's how they graphed it. They just graphed those ordered pairs that were given. Let's take a look at another type of graphing where they're actually going to give us a function in function notation. It says the maximum recommended heart rate, h for men, is a function of age a and can be calculated with h of a equals 214 minus 0.8a. And they want us to graph this function. So notice this output is the recommended heart rate. This a is the age. Okay, so what we're going to do is we're going to pick values for a, and we're just going to evaluate it. And I have a nice table here. So I put in 0, and I got 214. I put in 20, I got 198. 40 is 182. 60 is 166. And 80 is 150. Now, because I picked those values for a, and they weren't given to me, I'm going to use a continuous graph. So I have to graph all of these points, but I'm going to connect them with a line because somebody else may have picked 10 as a value, and they would get this point right here. Somebody else might have picked 50 as a value, and they would get this point right here. So I'm going to use a continuous line to show that these are the points that I picked, but somebody else might have picked something between it. So all of those points are actually on my function. I didn't do that last time because they gave me specific values that they wanted me to graph. So we have one more example, and this is when we actually have to create the function and then evaluate. So let's take a look. It says the Japanese bullet train that travels from Tokyo to Kyoto averages about 156 kilometers per hour. The distance from Tokyo to Kyoto is 380 kilometers. They want us to write a function to represent the distance remaining on the trip after a certain amount of time. So we need to remember that we need the distance remaining is going to equal the total distance minus how far we've traveled. That's what we're doing. So the distance remaining, I'm going to use function notation for that. I just did d of t. And after a certain amount of time, that's why my variable is time, and d represents distance. I'm going to take the total distance, 380, and subtract out how far I've traveled. Now it says it's 156 kilometers per hour is my speed. And if I do speed times the amount of time I've been traveling that speed, it's going to get me the total distance I have traveled so far. So that's how I got this. D of t, the distance, equals the total distance minus how much I've traveled. So now they want us to give the value for an input of 1.5 and describe what it represents. That just means take 1.5 and put it in anywhere you see a t, and actually just calculate this side of the function, 380 minus 156 times 1.5. So that comes out to be 146. And when they ask us to tell what it represents, we need to write 146 and 1.5 in terms of what these variables represent. So the 146, the result, is the distance remaining. So I'm going to say there are 146 kilometers remaining in the trip. And remember, t represents time in hours because our units are hours. So I can say after 1.5 hours. And you do have to specifically say the number and what it represents. You can't just say it's the distance remaining in the trip. That doesn't help. You have to say there are 146 kilometers remaining after 1.5 hours because it's more specific. Okay, so that's it for this lesson. Let me know if you have any questions.